Okay, so the ideal solutions and non-ideal solution. First, we will discuss. So, what are ideal solutions? Do you know what is ideal solutions?
Obeys Rawls law.
Yes. So, ideal solutions are those type of solution which obey Raoult's law. Its graph, right? And the ideal solution should have the following characteristics, like it should obey Raoult's law, which is PA equals to P naught A into X, mole fraction of A, and for component B it is P naught B into XP. Okay, and for ideal solutions, heat change on mixing is zero. Just remember that. The heat change of mixing will be zero in the case of ideal solution. Why? Because since there is no change in magnitude of the attractive forces, right? When the two components mix together, there is no change in the magnitude of attractive forces. That's why the heat change on mixing will be zero in case of ideal one. Okay? And in ideal solution, the volume change is also equals to zero. See, the volume of mixing is also equals to zero in case of ideal one. In ideal solution, the volume of the solution is the sum of the volumes of components before mixing. Okay, what is volume of solution in ideal one? Sum of all both the volumes of components before mixing. Okay, let's see the graph of ideal solution. This is a graph of ideal solution which follows Raoult's law, right? We have seen this graph in the previous lecture. This is for ideal solution graph. Here, this first and this second, this will show the PA graph. Just a second. This will show graph of first component, right? And this is the pressure of second component. And this line shows the P total pressure of the both the components. Okay. So let's see the examples of ideal solutions. So when we mix benzene and toluene, these will give you the ideal solution, right? And these solutions will obey this Raoult's law and this graph also. Okay, just remember the examples like for ideal solution, it is benzene and toluene, N-hexane and heptane. Another example is chlorobenzene and bromobenzene, right? And C2H5, your bromoethane, and this is your C2H5Cl, right? So these are the basically examples of ideal solutions. Okay, see, it's important that most of the dilute solutions behaves as ideal solution, right? Most of the dilute solutions, they behaves as an ideal solution. Means they obey the Raoult's law and its graph, right? And for that, the vapor pressure of the solution is always lies between the vapor pressure of the pure components. Got it? Clear? The ideal solution?
Yes, ma'am.
Okay. Next is your non-ideal solution. Now, what is non-ideal solution? Non-ideal solution do not obey Raoult's law. You know very well, right? And for such solution, delta H mix will not equals to zero, right? Either it will be negative, delta H will be negative, or either it will be positive. It will not be equals to zero. Same for delta V mixing, volume mixing, it will not equals to zero. Either it will be in positive or negative form. Okay, so the vapor pressure of these solutions are either higher, as in case of positive deviation, or either it will be lower. The vapor pressure will be lower, like in the case of negative deviation. Okay, and you can see the graph of the non-ideal solution. See, the non-ideal solution, it exists in two forms. It shows positive deviation as well as negative deviation, right? So see the solution which shows the positive deviation. Like for example, let's consider a binary solution, right? Let's consider a binary solution of two components, like component A and B. Okay. So what happens in positive deviation, the AB interaction, the A component and B component interaction, they are weaker than AA interaction, right? And BB interactions, right? So AB interactions are always weaker than AA and BB interactions, right? And see here, write down for negative here. This is for positive deviation. So what I said in positive deviation, see, delta H mix is always equals to is positive. In positive deviation, delta H mix of mixture will be always equals to positive, and delta V mix is also positive, right? And AB in this case, in positive deviation, what happens? AB interactions, the interactions of components of A and B interactions are weaker than those between AA and AB. Okay, so here you can see that the examples of a positive deviation, which is ethyl alcohol and cyclohexane, right? When you mix ethyl alcohol and cyclohexane, you will get the positive deviation type of graph, right? In which the delta H mix will be positive and delta V mix will be positive. Okay. Another example is acetone and benzene. Just like that, acetone and carbon disulfide is another example that shows a positive deviation, right? Ethyl alcohol and water, acetone and ethyl alcohol. So it's very important to remember all these examples of positive as well as negative deviation. Okay, and see one more thing. What happens in this pressure of first component, right? The vapor pressure of first component is greater than that of P naught A, the product of P naught A into mole fraction of A. It's always greater than this, right? Similarly, for PB, it is greater than P naught B into mole fraction of second component. Got it? Any question, bachcho?
No, ma'am.
No, ma'am, clear.
Okay, see, and just the reverse of this will be your negative deviation, right? For negative deviation, the delta H mix will be negative and delta V mix will be negative. And in this case, the AB interactions are stronger than those between AA and BB interaction, right? So what in positive deviation, what was that? AB interaction are weaker than AA and BB interaction, right? This was BB interaction. But in the case of negative deviation, AB interactions are always stronger than AA and BB interactions. Just remember that. Okay, now see the graph. So this is a graph. First graph is for the solution having positive deviation, and this graph is the solution which shows the negative deviation, right? So you can see that it doesn't follow or it doesn't obey the Raoult's law graph, right? So here in the positive deviation, what happens? This this line, this curves seems like that, just like that. This line goes above this ideal gas graph, right? This line, this is the graph. See, this line shows P total, right? And this shows the PA, not this. This one is for PA and this one is for PB, second component pressure, right? So this is a case of positive deviation. And what happens in the negative deviation? The uh, the vapor pressure of the solution line is this, right? This is the vapor pressure of solution. That is your P total. And this dash line shows the ideal vapor pressure of solution for ideal vapor pressure for solution for ideal gas, right? Basically, it shows the Raoult's law graph. This dotted line, this green line shows the Raoult's law graph, and this blue line, this shows the negative deviation, right? Which doesn't, that type of solution that doesn't follow the Raoult's law graph. Okay? Any doubt in this?
No, ma'am.
No, ma'am.
Okay. It's very simple. We just have to focus on the colligative properties, their formula, and the numericals, because most of the times the questions have been asked from that only. Okay, the colligative properties and want of factor and abnormal molar mass. The question came from there only. Yeah. See, what are azeotrope? What are azeotrope? Do you know? So see, azeotropes are basically the solutions of completely miscible liquids. Azeotropic mixture, when we talk about the azeotropic mixtures, so these are the solutions of completely miscible liquids which boils at constant temperature, right? And it can distilled over without any change in their composition, and that type of mixtures are known as azeotropes, right? Or we can say it as a azeotropic mixtures. Okay, so basically these are two types, like minimum boiling azeotropes. So what are minimum boiling? As the name suggests, the solution which shows positive deviation. Just remember that minimum boiling azeotropes are the solution that shows the positive deviations from Raoult's law. Okay, so these are called minimum boiling azeotropes. And because they have a composition which is having minimum boiling point, right? Because the name suggests minimum boiling azeotropes. So they have minimum boiling point. That type of azeotropes have minimum boiling point. Okay, so basically they have boiling points lower than either of the components. Like see, for example, for water, for a water, it is just for example, 100 degrees Celsius. Its boiling point for water is 100 degrees Celsius. And for ethanol, it is 78.6 degrees Celsius, right? And the azeotropic mixture formed from these two, it has a boiling point of 78.1 degree Celsius, right? Which is lower than both of these components, right? Ethanol, ethanol's boiling point is 78.6 and that of water is 100 degrees Celsius. But when the azeotropes which are formed from these two, you will get the boiling point to be 78.1, right? Which is lower than either of these components. Got my point?
Yes, ma'am.
Yes,
So
ma'am.
these are minimum boiling azeotropes. Next is your maximum boiling azeotropes. So what are maximum? The name suggests maximum boiling point, right? So already it means that they have boiling points higher than either of the components. Okay, like the and this type of solution shows negative deviations from Raoult's law, right? Negative deviations, and because they have a composition having maximum boiling point. Like for example, let's take an example of water and HCl, right? We are forming azeotropes of these components, water and HCl. So water is having a boiling point of 100 degrees Celsius, right? And for HCl, it is 20.2 degrees Celsius. But the boiling point of the resulting azeotropic mixture will be 108.6 degrees Celsius, which is higher than either of these components, right? So that's the example of maximum boiling azeotropes. Any doubt? All clear?
Yes, ma'am.
Yes, ma'am.
Okay, just remember that. Okay, next is your, which is very important, colligative properties. Okay, colligative properties we will discuss. So it is also known as democratic properties. So what are colligative properties? the properties of a solution which depends only on a number of moles of solute particles, right? The, this type of properties of solution, they will only depends on the number of moles of solute particles, right? But not on the nature of solute. These are called colligative properties. Okay, so basically there are four important colligative properties. First one is relative lowering of vapor pressure. Okay. Second one is elevation of boiling point. Third one is depression in freezing point. And the fourth one is your osmotic pressure. Okay, we will see one by one in details. Like first is your relative lowering of vapor pressure. So what is relative lowering of vapor pressure? So see, so in this case, what happens? The presence of non-volatile solute means that fewer solvent particles are at the solution surface. See here, there are very few particles are at the surface solution, right? So here the less solvent will evaporate, right? So less solvent will evaporate. So when a non-volatile solute is added to a solvent, when we add a non-volatile solute to a solvent, what happens to the vapor pressure? The vapor pressure of the solution gets reduced. And this phenomena is called lowering of vapor pressure. Clear? Got it?
Yes, ma'am.
Okay. Now see, according to Raoult, we know that Ps is P naught A, this is for solute, P naught A into XA
Yes, ma'am.
plus P naught B into XB, right? And if B is non-volatile, what happens? P naught B will be equals to 0 for non-volatile, right? The pure component vapor pressure will be 0. So what happens when you put this value into this? What will happen? PS will be equals to P naught A into XA, right? But in this case, XA is equals to, we know that XA equals to 1 minus XB, right? We know that XA plus XB equals to 1. From that, we can write down the XA equals to 1 minus XB, right? So just substitute this value. We have done this in the last session yesterday, right? So what happens from here? P naught A minus PS will be the lowering of vapor pressure, right? Now see, you don't have to worry about, just see the formula. How will you determine the molecular mass of solute from relative lowering of vapor pressure? Okay, so basically the formula for this will be P naught minus P upon P naught. This is equals to mole fraction of solute. And this is also equals to N upon N plus N, right? Now what is P naught here? So P naught here is, see where P naught here is vapor pressure of pure solvent, right? And P here is, what is P here? Vapor pressure of, this is for solution, right? This is for solution. And P naught A, see X here is mole fraction of solute, right? N here is, what is N here? Number of moles of solute, sorry, number of moles of solute. And what is capital N here? So capital N here is number of moles of solvent. Okay, you can write it just like that also. P naught A here is vapor pressure of pure solvent, right? Yes, here is vapor pressure of solution. And again, this is P naught A is vapor pressure of pure solvent, which is equals to mole fraction of the component, right? This is very important formula. And you can find the mole fraction of B, that is solute, to be NB upon total number of components, number of moles of all the components, right? So for every dilute solution, always the number of moles of B component will be lesser than that of A component. Okay, A here is solvent and B here is solute. Okay, now let's do this. Let's substitute this xp equals to, what is xp? Number of moles of solute. B, C, B here is solute. We are using B for solute here, right? So just calculate it for the solute. What is B? WB upon MB. This is the moles, number of moles, given mass upon molar mass. And this is WA upon MA. That is for solvent. Okay. So when you solve this, you will get this formula. You will get this formula. So from here, you can calculate the molar mass of solute, right? From the relative lowering of vapor pressure. Note down the formula. MB equals to P naught A into WB into MA upon P naught A minus PS into WA. This is very important formula. Written?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, this was for the relative lowering of vapor pressure. Just remember the formula, right? Next is your elevation in boiling point. Okay, now see, elevation in boiling point. So in this case, the boiling point of a liquid is the temperature at which its vapor pressure becomes equal to the atmospheric pressure, right? What is boiling point? The boiling point of a liquid is the temperature at which its vapor pressure becomes equal to the atmospheric pressure, right? So what happens when a non-volatile solute is added to a solvent? What happens to the boiling point? The boiling point of the solution is always higher than that of the pure solvent, right? The boiling point will be always higher than the pure solvent. Why? Because the vapor pressure of the solvent decreases, right? Vapor pressure decreases in the presence of non-volatile solute, right? And to make it boil, we have to increase the vapor pressure to atmospheric pressure, right? By raising the temperature. Clear? Just see, I'm repeating it. What I said is, when we add a non-volatile solute to a solvent, the boiling point of the solution gets higher, right? It is always higher than that of the pure solvent. Okay. So the vapor pressure of the solvent decreases in the presence of non-volatile solute. Just remember that. The vapor pressure of the solvent decreases in the presence of a non-volatile solute, right? And to make it boil, we have to increase the vapor pressure to atmospheric pressure, right? By raising the temperature of it. And this phenomena, this difference in boiling point is known as elevation in boiling point, right? And which is denoted by T, delta TB, right? So this is elevation in boiling point, delta TB. Clear?
Yes,
Is there
ma'am.
any doubt? If there is any doubt, please
Yes.
ask me in between. Just stop me and ask me, okay, ma'am, please repeat it out. Clear?
Yes, ma'am.
Okay. So see, this is the formula for elevation in boiling point. It's a very important formula. Delta TB equals to TB minus TB naught, right? So what is TB here? Delta TB is elevation in boiling point, and this is boiling point, and this is the pure component. It's okay. And also delta TB is equals to KB into M. This formula is also very important, right? So delta TB, you can find the elevation in boiling point using this formula also. What is KB here? Can you tell me what is KB here? You have done your 12th class, right? What is KB here?
Molar elevation constant.
Yes, good. It is molar elevation constant. Okay. And M here is molality. Okay. So
And the
elevation in
moles.
boiling point. Yeah. Elevation in boiling point is directly proportional to molar concentration of the solute in a solution. Okay. And yeah, molar, it can also be called as molar ebullioscopic constant. This formula is very important. Just remember that. Okay. So from the above equation, it is clear that elevation of boiling point, it depends on the number of moles of solute, right? But it doesn't depend upon the nature of solute. That's why it is a colligative property. Let's suppose that when we talk about if the molality is 1, so what will be the delta TB value? KB into 1, right? So the elevation in boiling point will be equals to the molar elevation constant when the molality is 1. So how will you define it? So molar elevation constant, how can you define it? Molar elevation constant is defined as the elevation in boiling point which is produced for 1 molar solution. 1 molar solution. Okay, so see, from this formula, you can calculate the molar mass of non-volatile solute. See, this is important formula, and you know how to calculate the molality, right? This is the number of moles of solute, and this is the mass of solvent in kg, right? This is in gram, that's why it is multiplied it by 1000, right? So you just have to take this weight in grams because you are multiplying it by 1000. And when you substitute the value of molality in this equation, you will get this equation. Okay, so that's how you can, when you substitute, from here you can calculate MB value, right? The molecular mass of solute, which is just substitute is just cross multiply KB into WB into 1000 upon, you will get delta TB into WA. By using this formula, you can calculate the molar mass of that solute. Okay, we will use in this in the numericals also, right? Okay. Okay, the next colligative property is your depression in freezing point. Okay, so what is depression in freezing point? So basically, the freezing point of a substance, what is that? It is the temperature at which the solid and liquid phase of the substance have same vapor pressure. Okay, so what happens when a non-volatile solute is being dissolved in a solvent? Its vapor pressure decreases, right? So vapor pressure of the solution is decreased. When the vapor pressure decreases, what happens? The vapor pressure of the solution will be decreased. It will become equal to that of the solid solvent at a lower temperature, right? And you can see in this figure, this is the graph of vapor pressure versus temperature. In this case, you can see this is for frozen solvent, right? This line is for frozen solvent, and this is for solution, and this is for liquid solvent. Okay, so what happens when a non-volatile solute is being dissolved? Vapor pressure decreases, right? Vapor pressure it has been decreased out, and also the for the solution one, the vapor pressure decreases, and it will become equal to that of the solid solvent, right? Which is at a lower temperature. So what we get is delta TF. What is delta TF? The depression in freezing point. TF naught minus TF. TF is your freezing point and your TF naught. Okay. So this formula is again very important. Just write it down. Written?
Yes, ma'am.
Yes, ma'am.
Yeah. Okay, good. So here, TF naught is the freezing point of pure solvent, right? Like for water, and TF is your freezing point of the solution, and delta TF is your depression in freezing point. Okay, you can all here one formula is also there. Delta TF is equals to AF into M. Okay, remember this formula also. And here, delta TF is your, the depression in freezing point. What is KF here? KF here is molar depression constant. Okay, and M is again a molality. So you can find the depression in freezing point using this formula also. Okay, now let's move to the next. And yeah, from this the above equation, similarly, you can find the molar mass of non-volatile solute. Again, this formula is important, right? So write it down. Write down this formula also. Just substitute the value of molality here, right? What is molality? Okay, number of moles of solute divided by the mass of solvent in grams, right? So you will, when you substitute these value in the this equation, you will get this equation, right? And after interchanging the delta TF and MB value, you will get the formula for molar mass of solute. By using this formula, you can find the molar mass of non-volatile solute. Okay, here's another colligative property, which is the last colligative property, osmotic pressure. So what is osmosis? Tell me, what is osmosis? बचपन से आप पढ़ते आ रहे हो, क्या होता है osmosis? मेरा, Sana, anyone?
Movement of liquids, fluids from higher concentration to lower.
No. Sana? Okay, see. So, okay. So the process of flow of solvent molecules through semi-permeable membrane from the solution of lower concentration. What happens in osmosis? The flow will be always from lower concentration to the solution of higher concentration. This is known as osmosis, right? Osmosis, the process of slow flow of solvent molecules through semi-permeable membrane from the solution of lower concentration to the solution of higher concentration. This is known as osmosis. And what are osmotic pressure? And the pressure which just prevents the flow of solvent molecules is known as osmotic pressure, right? The pressure that prevents the flow of solvent molecules is known as osmotic pressure. Right. In other words, we can say that the pressure that must be applied to the solution in order to prevent the passage of solvent molecules, right, into the solution throughout. You can add the throughout the semi-permeable membrane separating the two of them. Right, is called a semi-permeable osmotic pressure. As you can see in the figure, It is excess pressure, which is equals to the osmotic pressure, must be applied on the solution side to prevent osmosis, right? So, osmotic pressure, it is also colligative properties. Why? Because it depends on the number of solute molecules, right? And it do not and not on their identity, right? Not on the nature of the solute. That's why it is known as colligative property. Let's see, for dilute solutions, osmotic pressure is proportional to the molarity, right? C of the solution at a given temperature. So what is osmotic pressure? Pi is osmotic pressure here. CRT. C is your molarity, right? Concentration. R is your gas constant and T is your temperature, right? So pi equals to CRT. Remember this formula, pi equals to CRT. And you can also write, that the concentration molality is, what is, number of moles upon volume. Number of moles of solute upon volume of solution in liters, right? So what you can substitute this value in this equation and you will get I equals to N upon V. Just cut this. Just simply write the N upon V into RT. You can use this formula also. Okay, pi equals to N upon V into RT. N is the moles of solute here, V is the volume of solution in liter, R is gas constant, T is temperature, and pi is your osmotic pressure. We will use this formula to solve the osmotic pressure. Okay. Okay, the next topic is want of factor. What is want of factor, bachcho? What is want of factor? How we can calculate the want of factor? Okay, see. So simply to correct the colligative properties, a factor which is called a want of factor is used, right? And want of factor is denoted by I, right? And this want of factor, this accounts for the number of particles a solute dissociate into when dissolved in a solvent, right? And the number of particles a solute will be dissociate, right, into when it is dissolved in a solvent. That allows for accurate calculation of properties, right? So we have just discussed the colligative properties like relative lowering of vapor pressure, like osmotic pressure, right? Depression in freezing point, elevation in boiling point, etc. So to uh, um, correct that colligative properties, we use this want of factor, right? Basically, it adjusts the calculated value of a colligative properties. Okay. So what we can define the want of factor? Want of factor is defined as the ratio of particle concentration to substance concentration by mass when a substance is dissolved in a solution. Okay. So basically I equals to normal molar mass and upon abnormal molar mass. Now what is abnormal molar mass? Tell me, Mira, what is abnormal molar mass?
Ma'am, the molar mass which we consider before dissociation or association.
Yeah, okay. And you, Apsana, tell me what is abnormal molar mass? Apsana?
The incorrect molar mass due to the we calculated with colligative property.
Okay, okay. Okay, now see. Basically, abnormal molar mass is experimentally determined molar mass. Okay, and so what you have to do is just normal molar mass divided by, and they just divide it by abnormal molar mass. Now, if a uh, if a molecule dissociate, right? When dissociation will happen, then the value of I will be always less than 1. Okay? Value of I is always less than 1. And for association, I is always greater than 1. Okay? And for just like the number of, if there is no association or dissociation, so the value of I is equals to 1. Just like C. See, for example, if I tell you to calculate the value of, uh, tell me, NaCl. What's the value of I? Want a factor for NaCl? Okay, I think is, see, it's just reverse of the, just a second. See, for if the value of I is equals to 1, is greater than 1, so the solute will undergoes dissociation, right? Right? And if the value of I is less than 1, then solute will undergoes association. Just remember that. Okay. Just like let's take example of NaCl. NaCl, it will dissociate to form Na plus and Cl minus, right? It will dissociate to form sodium Na plus and Cl minus. So you can see that NaCl, it will dissociate to form two ions, one for Na plus and the second ion for Cl minus. So what will be the value of I? The value of I will be 2. Okay. And see, just for CaCl2, what will be the value? Right, just dissociate this. Just dissociate this.
3.
Yes, very good. It will 3. And just tell me what's the value for C12H22O11? What's the value for one factor for this, for glucose?
1.
1, 5.
Because for glucose there is no dissociation or association.
Yes, good. Right. So there will be no dissociation or association. So that type of non-electrolyte, it's the Water factor value will be always 1. Okay, got it?
Yes, ma'am.
Yes, ma'am.
And yeah, uh, let's see. Yeah, see for degree of association, you can find the degree of association using this formula. This is alpha equals to I minus 1 upon 1 minus n minus 1, right? So this is the formula for degree of association, where alpha is your degree of association, I is your want of factor, and here n is your number of solute molecules associating to make a bigger molecule, right? So this is the number of solute molecules which are associating. right? To form a bigger one species. And for degree of dissociation, this dissociation is like so. You can calculate the degree of dissociation using this formula I minus 1 on m minus 1, right? So again here m is your number of particles which are formed per molecule of the electrolyte, right? This m is the number of particles which are formed per molecule of the electrolyte. So these formulas very, very important. From there, questions has been come in your JEE mains exam. And see, and the inclusion of Wanter factors, these modifies the equations for colligative properties also. Like for elevation in boiling point, we use P naught equals to, in every formula, just multiply it by I factor. It will give you the correct value of the colligative property. And for elevation in boiling point, delta TB, which is equals to I into KB into M. Similarly, for depression in freezing point, it will be I into KF into molality, right? And for the fourth one, like for osmotic pressure, it will be I into C. Like concentration, you can write it by N upon V, right? Number of moles of solute upon volume in liters into RT, right? So these formula we will use in the numerical part. That's all about the solution chapter. We have covered all the important topics over here. Now, there are some questions, right? Previous year questions we will discuss. Okay. So there are some previous year questions. Can we practice these questions in today's session, or we can take this in the next session? Tell me, can we extend the class? It's already 10 p.m. Meera and Apsana, tell me, बच्चों.
Ma'am, can you repeat? Your voice is lagging.
Okay, I said, is there any, can we extend the lecture just like 10 to 15 minutes to solve these problems, or we can take this questions in the next class? Like tomorrow, we can solve these questions. We can take one session in which we will do the all the previous year questions from the solution chapter only. After that, in the next session, we will start the chemical kinetics. Tell me if you are comfortable to extend the session. I don't have any problem. Okay. Okay, no problem. I think you guys are tired. Okay, so for today, uh, we have completed the solution chapter. Based on these topics, we will do some important previous year questions. Okay, of JEE Mains. So please be prepared for tomorrow and just revise all the concepts of solution chapter. All the formula, all the concepts, just revise it. Okay, any doubt from the today's session? Please tell me. Let me know if there is any doubt.
No, ma'am.